Hi everyone, my name is Christopher Selolo. One of the UNISA student doing one of the student doing WRP 4801 as a subject, and my student number 59106292. Yeah, today I'll presenting my WRP 4801 assignment project. The project is titled Hydraulic Flood Simulation of the PONGOLA River using HEC-RAS. The purpose of this study was to investigate how the PONGOLA River behaves under different floods conditions using HEC-RAS hydraulic modeling software. The project also evaluates how changes in channel roughness affect flood behavior and river hydraulics. Flooding is one of the most common natural disasters and can cause serious damage to people, infrastructure, and the environment. Engineers usually use hydraulic modeling to predict how river will behave during flood events. In this project, HEC-RAS was used to simulate different flood scenarios in the PONGOLA River. The model helped us to understand changes in water levels, flow velocity, flood extent, and overall river performance during floods. The objective of the project was to evaluate the hydraulic behavior of the Pongola River using different flood conditions using HEC-RAS to achieve a hydraulic model of this river was developed using 11 cross sections. The model was then used to simulate a flow of 3,200 cubic meter per second, and the other condition was the one in twice in 100 years. The other one was twice in 300 year flood. Finally, and then the effect of increasing Manning's roughness coefficients by 62% and 92% was investigated to determine how channel roughness influence flood behavior. So in the scenario 1, the first simulation used a discharge of 3,200 cubic meter per second, and the results showed that the river was able to carry the flow safely within its banks, and then water levels remained relatively low and no flooding occurred at the selected cross sections. The flow velocity ranged between approximately 2 and 3 meters per second, and the Froude number remained below 1, indicating stable subcritical flow. Overall, the river performed well under this normal flow condition. In scenario 2, which is the second simulation, represented a flood that has 2% chances of occurring in a year. Compared with the previous simulation, water levels increased significantly and the river operated much closer to its capacity. Flow velocity also increased, reaching values of approximately 4 to 6 meters per second, although the river remained stable. The reduced freeboard indicated that the risk of flooding had increased. In our third simulation, represented an extreme flood event with a very low probability of occurring in any year. This scenario produced the higher water levels, the greatest flood extent, and the highest flow velocities. The river channels remain stable, but the water surface approach the top of the river banks at several locations. This scenario represents the highest flood risk and demonstrate the importance of designing hydraulic structure that can safely withstand extreme flooding events. We did another analysis, which is a sensitive analysis, was carried out by increasing mining roughness coefficient by 62% and 90%. Increasing the roughness made the river channel more resistant to flow. As a result, water level increased slightly while flow velocities decreased slightly because of greater friction. Although the river remained a subcritical flow, the reduced channel capacity increased the potential for flooding during larger flood events. Um, the overall findings in total results show that water levels, flow depths, and flood extent all increased as the discharge increased. Larger flood events also produced higher flow velocities and greater hydraulic energy. The froth number remained below 1 in all simulations, confirming that the flow stayed sub, sub, subcritical and hydraulically stable. The study also showed that mining roughness is an important factor because of it influences both water levels and flow velocity. Thank you.